This video is made about automation and control. So we have learned about signal transmission, 420 milliampere signal loop, and how the signal generated from the sensor is displayed in a display unit to either use for control purposes. Now, this circuit is basically designed to display the water level of a tank, right? So the sensor is used is a load cell. Now this is the load cell, right? This is you can see here says 10 kilogram, right? 10 kilogram load cell, and you can see this whitish color, right? So here the sensors are there, and there are 4 wires are coming out. So now the load cell is a device where the load can be measured, right? And so it has a sensing device is a strain gauge. Actually there are 4 strain gauges configured in the way of Wheatstone bridge. So we have learned about Wheatstone bridge. So when we give a supply to the Wheatstone bridge and depend on the resistance value variation, we can get a output. Now here in the strain gauge, black and red, the supply wires, others are the output wires. So Wheatstone bridge is here made out by strain gauges. And now so basically these are commonly used in marine applications for cranes, right? So we will see how this signal is taken and bring up to the display unit or the control unit. Now this load cell generates maximum about 5 millivolt output. So the 5 millivolt output is very low. It is extremely low output. So we can't do anything with this output without properly amplifying it. So we have to use a instrumentation amplifier. So the instrumentation amplifier is here, right? It is in this IC, right? This IC is used as an instrumentation amplifier. So this is a power regulator, the voltage regulator IC. So it supply this circuit, power supply to this circuit. So this is the instrumentation amplifier. Now when the instrumentation amplifier amplifies the voltage, right, this 0 to 5 voltage, 0 to 5 millivolt, then we have to transmit this signal into a another place, right? It may be quite far, maybe 300, 400, maybe 500 meters away from the sensor or nearby, wherever. So we are using here 420 milliampere signal method. Now you guys know that when we use a sensor, right, then sensor has to be connected to a transducer. The transducer is the one which converts the signal given by the sensor, right? In this case, the load cell, the basically variation of the resistance, right, is converted into voltage by the Wheatstone bridge. But in some cases, if you use a PT100 to measure the temperature, in that case we don't have the Wheatstone bridge device at the engine side. And the older system, yes, we use the Wheatstone bridge and it is kept in the control room and all, but nowadays we don't use that system. So what we are doing, we use a transducer. So what does the transducer do? The resistance variation is converted into either voltage variation or current variation, voltage or current figure. Now as example, the voltage standards are 0 to 5, 0 to 10, right? And those are the standard of 2 standards out of many. And the current standards, most popular is the 4 to 20 milliampere current loop. And 0 to 20 also still in use, right? Of course 4 to 20 is in use. So now here what I have used is the 4 to 20 milliampere current loop. Now this is the circuit right, which responsible to generate 4 to 20 milliampere proportional to the variation of the input. And this is this is a IC which used to manipulate the signal which takes from the instrumentation amplifier, and this is the amplifier which generate real 420 milliampere signal. So this amplifier IC, this is a transistor, and this transistor is driven by this IC, and this IC receives the signals from the instrumentation amplifier. So the instrumentation amplifier is connected to the sensor. So sensor, instrumentation amplifier, then the 420 milliampere drive IC, then this is the amplifier. So you can see this is basically a transducer. Now I have connect this circuit, the transducer, into the display unit. You can see here there's a display unit which is having 40 LEDs, and this display unit also having several ICs, say 1, 2, 3 and 4 ICs to drive the LEDs, and this is the power supply regulate IC, and this is a very important IC which I want to explain. This is the error correction IC, right? The error correction is related to this IC. So now 420 is generated here, it is given to the receiving end. So these two devices might be maybe 300-400 meters away from each other, right? Even more than that. So now you know that one of the highest advantage of 420 milliampere signal loop is it is immune to any external voltage variations like inducing of the voltage and the variation of the resistance of the cables due to especially temperature when the cables are long. So the 420 milliampere signal loop is immune to those. So now here as I told you before, this is the display unit, right? So now what I have done here, I have not connected the load cell yet, right? Because with the load cell I cannot simulate here on the table because I have to give a 10 kilograms load and it is quite practically difficult. So what I did, instead of that I made a simulation signal. Now this is the simulation signal generator, right? And now you know that in control systems, to find the faults we have to calibrate various devices. First the sensor, then the transducer, then the receiving unit, right? Likewise one by one we have to calibrate. So when we calibrate those units, so we have to give signals, right? So this is actually something like that, right? So instead of the load cell, I have employed that potentiometer. So we will see the faults in this system. So we have learned that there are basically 3 faults, the errors basically, right? Now the faults, we call those errors in the system. One is zero error, the other one is the span error, and the third one is the linearization error. So this linearization error generally in most cases we cannot correct, but with modern electronics, yes, we can, right? And the zero error and the span error, anyway we can correct those, right? So I will now forget about this load cell and all. Now assume that this is a boiler water level controller, right? Assume that this is a boiler water level controller and a display, right? Controller and a display. Now I will simulate the signal which is given by the DP cell. You know that there's a DP cell to transmit the water level signal to process by the other units. So the DP cell signal is simulated by this potentiometer, right? This potentiometer. So I will turn this potentiometer, and you can see when the potentiometer is touched, these LEDs are, you know, running up and down. So that is normal because this is a very sensitive circuit, right? So once I release my hand, it goes off, come back to normal. So now I will drain the boiler, right? So when the boiler is drained, what happened? The water level, it goes down. Now you can see the yellow lights are gone. Now green lights are going one by one, right? Green lights are going on, sorry, green lights are going one by one, right? So now this is the zero water level in the boiler. Now you can see, not in the boiler actually, the measuring column, right? You know, in the gauge glass, in the center it is 0, then plus 10 and minus 10, right? This is minus 10. Now it has gone to minus 10, and so in this case 0 is here, plus 10 is here, minus 10 is here, right? Although the boiler water level has gone to minus 10, here display is showing minus, say, about 9. Now there is an error here. Now we have to eliminate this error. Now we have discussed about the error correction with the graph and all. So you have to draw a graph to correct the errors, right? So I will show you the graphs which I have drawn to eliminate the errors of this. Now this is a graph, right, and which I draw about the transducer, right? So you can see initially there's a error, right? But there's no linearization error. It is linear, very linear, right? But there's a zero error, right? If there's not a zero error, this line must cross at 0, 0 point. Now there's another graph. Now here, this one. Now this is to calibrate check the display. Now there's no error here, right? There's no error, no zero error, no span error. It is perfectly calibrated now, right? So we have to make a graph like this, which we have already discussed about it by handouts. And when we make the graph, so we find an error. Now error is displayed here very clearly. So the boiler water level is at the minus 10 of the gauge glass, but here it is showing, say, minus, say, 9 around. Now when the errors are corrected, first of all you have to correct the span error, then the zero error. Because if you correct the zero error first and then if you go to correct the span error, again you get a zero error, right? Again you have to do the zero error correction. So there's no point of doing that. Then you have to do the first you have to do the span error, then the zero error. So now this error is there, right? But I will correct the zero error first, right? And to correct the zero errors, there are a couple of ways. And this is the 420, right, signal generator. And here you can see the variable resistors, right, small potentiometers. So we call those presets, right? By turning these two, we can do that, right? Actually, we had one is to correct the zero error, other one is to correct the span error. And here also you get two pots, right? So this pot is to correct the span error, and this is to correct the zero error. Now as there's a zero error, right, I will correct the zero error, but remember that first you have to correct the span error, right? As this is a demonstration, I will correct the zero error. And so you have to turn this pod, right? So now the error is increased because I turned it to the wrong way, right? Now I turned it to the correct way. right? You can see the error is eliminating, right? Now the error is gone, right? And now let's see. Now the boiler water gauge loss also -10. Now here also -10. It's perfect condition. Now we are filling the boiler now once again, right? So the water level is going up. So I'm generating the signal, input signal. So you can see the water level is slowly going up. Now it has come about half the way, right? Say right. Now the level of the boiler is at +10 of the gauge loss. Now what has happened? Now the 0 is correct. We know that the 0 error is done. 0 is matching, but +10 and +10 is not matching. When the boiler is at +10 and here maybe +8, right? So we have to correct this error. Now this is basically the span error shown here, right? This is the span error shown here. And now to correct the span error, so we have to manipulate with this potentiometer. Now I'll turn the potentiometer and we'll see what happened. These are very sensitive circuit, this is. So let's see. Now you can see that is being increased, right? Okay, right. Now at the boiler, the gauge class, it is +10, and here also it is +10, right? Now we will try it once again. So I will generate the signal and I will turn the signal generating potentiometer, and I am reducing the boiler water level. Now you can see the boiler water level is getting reduced, right? So now here actually we consider only the bottommost value and the topmost values, but we have to consider that we will get the calibration of the middle points, same as which I have done here, right? So this is the table, right? Several points have been taken. Likewise, you have to take the several points, then only you can decide whether there is a linearization error or not, otherwise it is not possible, right? So I am reducing the level. So the level is reduced now. Well, now the level is minimum. Minimum is -10. You can see there's an error here now, right? So when we manipulate with the span potentiometer, this error has been introduced. So this error has to be eliminated now. So to eliminate that error, this is a 0 error basically, as I told you, right? So we have to correct the 0 error now once again, because we followed the wrong method. Because we initially corrected the 0 error, then the span error. Now things have gone wrong. Now we have to come back to 0 error once again, right? So now this is the 0 error adjusting potentiometer. So the error has been reduced a little bit, right? Right, the error is eliminated. So now we will see the performance of our job, whether we have done it correct or wrong. So we have to do the same thing once again. Now in the potentiometer, I am turning now to reduce the water level, and you can see the display level also getting reduced, right? And so this temporary variation of the level when I touch the potentiometer, so it happens, but when I release my hand it becomes normal. so nothing to worry. So I am reducing the level once again. So now it is in the red area. So now it is not showing anything. So now the water level has come to minus 10 in the gauge loss. So we can try it once again to going up, right? So now it is increasing, right? Now it is increasing halfway around. And okay, it is in the yellow region, right? Now the locally at the boiler side it is plus 10. Now here also it is plus 10. The job is done and the performance have been evaluated. Now just for your knowledge, but this is not much required for your examination purposes, but I will show you this circuitry. So this is the instrumentation amplifier which I have used, right? And this is the 420 milliampere current loop. So this amplify 0 to 5 millivolt up to 0 to 1 volts, and this guy converts into 420 milliampere. This is the transistor which amplifies and which generate this 420 milliampere signal. So this is the error correction circuitry, right? And you can see there are two potentiometers, right? So this potentiometer is to correct the span, and this is correcting basically the gain of the op amp, and this is to correct the zero error. So I believe you have understood the basics. So if you have any questions, you can contact me anytime. Thank you.